So hello friends, this is the last video of VESTA series lattice mismatch. So I have created the structure of graphene and HBN, in which I showed that how we have reduced the lattice mismatch between graphene monolayer and HBN monolayer by using en route integer method. Now this is very important topic or very important system that may or may not exist, but because we are working on something that has to deal with the creating structure, so you will have different kind of structure which could have a different lattice mismatch. So you have to find out the best possible system or number of atoms that can work for you and that can give you a reliable computational results. So let me just remind you something that the maximum lattice mismatch was coming from monolayer of titanium sanides and gallium nitride, which was approximately around 45%. So this system, if we'll try to do computational study, it will have a very it will show a difficulty in convergence, and it might not converge. So what we can do is we can again use our root integer method, and the matrix you have to type is -23125005, and let me just now show you how I can just create an how I can use this matrix to create the structure. So first let me just go to gallium titanium heterostructure. So I have the monolayer files. I will just drag it one by one, and I will show you the lattice constant. There is another way you can just check the lattice constant. It will be printed here. So it is around 3.26, which I usually take for gallium nitride. Similarly for monolayer of titanium, if I take it, it will be around, I think, 5.26, if I correctly remember. It could be yeah, if it is 5.9. So it is a very, like, you can say the difference between their lattice constant are very different. So it will end up with a structure which have a very high percentage of lattice mismatch. So how we can just work in that, I will just start with the option called edit. I will go to unit cell, then I will transform it, and I will use my this matrix -√312. And the reason I am using is I have like hit and trial method. I try to find out, and there is a very good course in that. So the same, however the structure is with the bilayer, so I just thought let me just make with the monolayer. So just make it a search for atom. Okay, so now I will just do okay, and I will save it as an direct coordinate. The reason I am not, I can also save it as XYZ coordinate. There is no difficulties in that, but in general I try to just save it in the direct coordinate when I am just creating the heterostructure. Now I have already saved this file, so I have given a root 7 name to him. So I will not just show this, I will not just save this file. So okay, but for like transparency, I could save it with DC1. So let me just Cartesian, okay, fraction coordinates I will just check. Let me just now just see this file. Now we have 15.64 lattice constant. I am just taking a value. You can take you can, means you also should take this value, and then I will do the same thing with gallium nitride. I will go to this structure, I will edit, and I will just go to unit cell, I will just transform it, and I will just type 5 and 5. Now as I have typed 5 and 5, and go to this settings, search atom and unit cell and apply. Now I can save it. I have already saved it, but let me just explore it, and now I have like monolayer of, like, it's, I have given just name 5 to it, so there is no, like, you can always save it. Now let me just show this file, monolayer of gallium nitride. So gallium and nitride, there is a 25 atoms. So what we can do is, we have heterostructure of this system, and I will just type copy, and I will just write heterostructure created root I integer method. Now as we have this structure, now what we can do is, we can just take the coordinates of gallium, and I can just save it in that file. Now we have like Control C, and I will just save it in this file. The good part is, okay, let me just check it. Okay, so I will save it here, paste it here. Now I can write gallium and nitrogen, and then I can write 25. Please mind the voices, because I am recording this without a fan. However, I don't have control over construction, because it is going in my near to my house, and I have tried to reduce it, but it is like sometimes things you cannot control. But it's a, we have to just focus on learning, not the distractions. So good part is that it is now pasted on that. So let me just do a very good thing in this. What I will do, I will just save it as an XYZ coordinates. Reason I am sharing it, like saving it, is now like we have to just, you can say, we have to like separate the different coordinates. Okay, now we can just see our file. Okay, is it separated? Yeah, it is separated. I will just write 14, and I will just add some vacuum. Vacuum is important. Vacuum is important because then you have to like make a difference between two structure. So now you can see there is a vacuum in the Z direction. Now what I will do is, I will just take these coordinates and I will just paste it here in my file, in my Excel file. This method I have already shown. So Control C. Good part is that Control C is working, and if I just paste it here, you will see no change. I have already pasted it, so there is no change. There will be no change. Now the important thing come from now. Now, like I have already labeled, like we have a 21 titanium and 7 SN and 25 gallium and 25 nitrogen. From gallium, what I will do, I will use this command, like I will just select it and then add 4 into it. Why I am doing it? Because I have to like make an at least 8 angstrom distance between these two structures. So now I will just paste it. I will just copy it. Control C I will do, and I will just paste it here, and then you will see the magic. Now Control V is there, and let me just show you the magic that happened. And I will just drag this file again to VESTA, and you can see now. the files are separated. And however, now you will ask, what is the lattice mismatch between these two monolayer? I have already calculated. So let me just show you these two numbers. So if you just take the monolayer of gallium, it is around 16.8, and if we take the monolayer of this system, it will be around 15.64. and the good part is, if we just see the difference, it is around 2.55%. so hope you can see that the lattice mismatch has reduced to 2.55%. however, you can also do the reverse. If you are just pasting it, it will be maximum around 2.55%. so if we compare with this file, it is 45% to we are reduce it to 2.5%, but the cost is we have more number of atoms in our VAS file. So the people who have the good computation power, they can use this method. However, the people which have a very less computation power, it might not help. But anyway, it's a general way of reducing the lattice mismatch in VESTA. So I hope you like this video. Thank you very much, and keep liking and subscribing to my YouTube channel. Share with your friends. I think this lattice mismatch series is now over. I will just move to nanostructures and the other kind of structures that is we can make made in VESTA. So thank you for liking, and keep learning.